Ladies and gentlemen, welcome in AGH Aula, and we have a special occasion today. I would like to welcome our special guest, Professor Alberto Sangiovanni-Vincentelli, who is a honorary guest today, and I also would like to welcome our guests, Professor Jan Tadeusz Duda, who is chairman of the Parliament of Małopolska region, and I would like to welcome also Professor Gorzałek from the Jagiellonian University, the Dean of the Department of Electronics and Informatics, Professor Sławomir Głuszczyński, and other professors and colleagues from the university. I would like to say that the event is now transmitted by YouTube, and because of the pandemic, we are in the limited number of people here, but I hope many of participants are online, so hello to everyone who is online in the distance mode. I would like to introduce Professor Alberto Sangiovanni-Vincentelli, who is a distinguished scientist with a tremendous track record in research, innovation, and technology development. And he is chair of the Electrical Engineering and Computer Science Department at University of California at Berkeley. He is co-founder of Cadence and Synopsys. We know these software tools very well. Professor Machowski is for a long time a representative in Eurochip, and now is also responsible for cooperation with this company. And Professor Vincentelli is also the member of the board of director of Cadence and many other companies. I have many names at this position, but I would like to say that all of us are very important one in electronics business, and congratulations. Professor Vincentelli is a member of the advisory board of Walden International, XZ, of the scientific advisory board of the Italian Institute of Technology, and the chair of the strategic board and of the international advisory board for the Milano Innovation District. He is a member of the advisory board of the Politecnico di Milano and honorary professor at the Politecnico di Torino. He was the president of the Comitato Nazionale dei Garanti della Ricerca and of the strategy committee of Fondo Strategico Italiano. He consulted for companies such as Intel, HP, Bell Labs, IBM, Samsung, UTC, Lucent, Kawasaki, Steel, Fujitsu, Telecom Italia, Pirelli, General Motors, BMW, Mercedes, and so on and so on. As you can see, there is a person who is very well recognized in the world. Professor Vincentelli is an author of 19 books, 2 patents, and over 1,000 scientific papers. He is fellow of IEEE and ACM and a member of the National Academy of Engineering. He earned IEEE Maxwell Award for groundbreaking contributions that have had an exceptional impact on the development of electronics and electrical engineering or related fields. And many other awards, which is listed here, and we hope the next special occasion will be tomorrow. The honorary doctor of the AGH University of Science and Technology. Professor Vincentelli, the floor is yours. Please give a lecture for us.
Thank you very much for such a wonderful introduction. So I'm sorry that they gave you the full spiel. In general, when I go and give presentations, I just say, Alberto from Berkeley, and the story. But it was a nice recognition from you all to list my accomplishments. Now, as we were saying before, in the rector's office, most of the accomplishments are due to luck, right? I am not just making it up. Is that you have to recognize that what happens in your life is very much a consequence of chance, right? Where the ability comes in is to recognize that you got a lucky break, right? And so to make the best out of it. And so if I look at all my life has been a subsequence of these events, and then some went well, some went not so well, but overall went pretty good, right? So for the young people in this audience, never give up and look for your chance, and be courageous, take this chance. Anyway, so today, I've done much of my work in design methodologies, but not only for integrated circuit, but also, as the rector said, I've done a lot of work in other fields, especially automotive. So since 1988, I work in that field. Is immediately after we founded Synopsys. So at some point I said, well, what can I do in addition to integrated circuit? And automotive happened by chance because the CEO of Magneti Marelli, who is an important tier 1 producer, came to Berkeley and said, well, you are good at design and all of that. We have a problem. I said, okay, what is the problem? They co-invented the semi-automatic gear shift, 1988, right, for Formula One cars, and in particular Ferrari. So he said, well, I'm not sure that it will work, and if it doesn't work, the pilot will die. So, okay, that's not small feat. And so he said, well, help us out to verify if this thing will work or not. So we did. It was difficult, not easy at all, because in 1988, the processor that people use in automotive were small and not powerful at all. And so all the programming was done in assembly language. And so the first thing that I learned when we did the design of integrated circuit is that you have to understand what you want to do first. And then you have to find the best way to do it, right? So the what and the how. But you have to keep them separate. Now, if you ask to the guy who invented this semi-automatic gear shift, what is the algorithm that you use? Because it's much simpler to verify something works at the beginning. It becomes more and more difficult. And it also has very negative impact if you find an error too late in the design process. Well, he came up with this stack of paper, and it was the assembly code, right? And I said, okay, now, how do I get back the algorithm from here? So we had to do reverse engineering, and we were able to find this algorithm. We found a problem, and so all of a sudden, people start talking to me in the automotive industry. So I started working with Mercedes first, then BMW for 5 years, and then for 13 years with General Motors. And the whole scope of this work was to improve in the way in which cars were designed. Now, one of the things that was very clear in the Science and Technology Advisory Board of General Motors, where I was sitting, that would report directly to the CEO of General Motors, that automotive sector was ready for a disruption. So General Motors knew. They knew that something was going to happen. Not when, but it was very clear that something was going to happen. It did happen, right? And it's what we are living today. And the interesting thing was that the common wisdom was the Silicon Valley is going to do something, right, in automotive. And notice that in the years, like 10, 15 years ago, the idea that companies in Silicon Valley could do automotive was kind of remote, right? So why should they worry about mechanical system like a car? In fact, they didn't. The entry point of the Silicon Valley company was not the mechanical, was the electrical, and was the electronic, and was the software. But now, that is where the battleground is. So this is another lesson that I learned. I worked for many years with IBM. And what happened at IBM was the same kind of worry. Something is going to happen. Something is going to happen. And we may not be relevant anymore. The point is that when you have a huge company like IBM and General Motors, to change course is very difficult. It's like the Titanic with the iceberg in front of you. You see it, but you cannot steer. It's too big, right? And so that is one of the reasons why innovation is, in general, difficult for a big company. It's not difficult to do research for them. Actually, it's easier than for other companies. But it's difficult to bring this research into actual working products and the like. And the reason is, again, is the fact that you have a huge market. Anything you do is like a drop in the sea. And there is a lot of fear that this drop in the sea may not pan out. And so most of the way in which established companies in the United States do innovation is through acquisitions. So you buy a company, a small company that had some brilliant idea, so that you can incorporate that into your company. Now, how many acquisitions in general in the United States? Huge amount of acquisition, very large numbers. How many of these acquisitions have had success? Very few. But some did, right? And so the acquisition market is still very active, especially for medium-sized companies. And so that's a dynamic that you encounter that help explaining some of the things that happen even in the automotive market. There is one such acquisition that seems to be working, is the Cruise company that was acquired by General Motors. And actually at that time, when I was working with General Motors, they never been to, some of the top-level management, never been to Silicon Valley. So I had to take them and say, show, see. And I remember a very famous venture capitalist told the GM guys at dinner, you should move to Silicon Valley. So the headquarters, no more in Detroit, Silicon Valley. Well, in some sense, the Cruise acquisition is having an effect on the makeup of the management of General Motors. So maybe General Motors can be a player in what is happening today in the industry. So this is kind of a long introduction, but now let's get into the heart of all of this. So the first thing is that we have to look at, and I have one slide that represents like 50 years or more of evolution in the electronic sector in general, so the information technology sector. So at the beginning, when I graduated, we had big computers, but not big in terms of powerful, big in sense of large, right? And then if you look at the power of these computers, it was very, very small. One, was 1 megabit instruction per second. Now it's like, come on, give me a break. 1 megabyte of memory, so and very huge, right? And so the way in which we interacted was through punch cards, right? That was the interactive terminal that we were using. So fast forward, now what do we have? Now we have the era of the internet or the interconnected devices. So laptops, cell phones, and all of that, which has democratized the use of computing. But the future is going probably to be this one, right? So it's the swarm system. So essentially, lots of sensors connected together, smart sensors that work to bring new products, new ideas, new way of living to the market. And of course, all of this is empowered by the cloud, where most of the heavy-duty computation occurs, right? So that's the new world. Now, what is the impact of this new world? And sensors can be as scary as the one kind of bed of nails that you see on the corner. What is that? That is actually a sensor that you place in the brain of people. So the spikes are so small that are infinitesimally smaller than a neuron. and so the neurons don't die if you connect them to this device. But it shows that even a person could be calm and node in this infrastructure that we call the information technology infrastructure. So we already see this, for example, for people who have severe impairment, right? So people without a limb, you can connect directly the brain to the mechanical arm, and they feel like they really have their arm. There's no difference. You can connect to, you can affect the way in which our brain works. In the case of diseases like Parkinson, some say even Alzheimer, I doubt it, but certainly Parkinson, and phenomena like severe depression. This is called deep brain stimulation. So you just put some small currents in the brain. It's like a reset of the functioning, electrical functioning of the brain. So it is possible, it has been done, and it is scary that you could use this technology in negative ways, call it, right? Okay, so one of the things that we forecasted a few years ago was that the computers and cell phone will disappear. Why? Because of these sensors everywhere. So you see me with this funny thing in my ear. Well, if you imagine in the future, where is going to be the microphone? In the walls, right? And it's going to amplify my voice. Do I want to project an image? I will have an hologram. I'll do like this to change. Next slide, boom, next slide. So is in this scenario, the center comes back to be the human, right? Even though it's super amplified, but everything that is around it. Now, remember that there has been a significant event in the past few months, and it's the fact that Facebook has changed its name, right? It became Meta, right? And the name of Meta is related to the metaverse, which is this virtual reality world, right? And how is that possible? Because of this evolution of electronic devices and of electronics. Now, one thing has become clear in all these last years is that software is important, definitely, is the way in which you make devices work, but you cannot forget about the electronics, the actual physical devices, because it's a combination between physics and the computing that makes a difference. So much so that we call this kind of discipline cyber-physical system. Cyber implying, brain, implying software, and physical implying the physical aspect of this, or CPS, okay? It's cyber-physical system. Okay, so this is having an impact, very large impact, on today's economics, because Facebook has invested a ton of money into this. Now, we had, you see that little glasses, that was proposed like maybe 7 years ago by Google, right? The glasses, the Google glasses, right? So it was the first manifestation of this kind of evolution. So, well, the outline is that we are going to say how the car is changing fast, and it's going to become something that we have not seen before. Because of the autonomy, which was a big event about 10 years ago, that people started thinking or imagining that you could have cars that drive by themselves, and this was the key for the Silicon Valley company to come in. The investment in electronics, as we said, not only in the software but also in the hardware side, and in the methodologies to put these things together. We're going to look towards the end of the talk and what kind of economic disruption this technology is going to bring in. And then we're going to touch upon two very important issues about autonomy in general, not only cars, but airplanes and everything, which is ethics and security. And we'll see in what sense ethics has anything to do with this. So what is the evolution of the automotive DNA? So the traditional car, how is it built? It's energized by petroleum, is powered mechanically by an internal combustion engine, is controlled mechanically, is a standalone device. It has a full dependence on the driver, and the last one is typical of automotive designers. They think about the use of the car. So is it going to be to transport passengers, to transport goods, or what, right? So that is in general is intended for a single use. Recently, you have seen these crossover vehicles and all that are trying to have multiple usage. But the new DNA is for sustainability is going to be, of course, is electricity and hydrogen. And we know how much investment the car companies have made in the electrical domain. Most of the car companies have said that by 2030, everything they do is going to be electric. And so the internal combustion engine is going to disappear. Some people start using hydrogen. And hydrogen is a very effective way of transporting and using energy. So it's likely to have an important impact. Not now, not yet. Then, of course, everything that is in the car is going to be powered electrically, so there is no more mechanical controls or actuation of the commands. And it is going to be connected. So all the cars that are running in our streets are going to have direct connections, not only through the cloud, but among themselves. So everything is going to be considered as a whole. Semi or full autonomy, that sometimes is a dream, sometimes is a reality. Definitely semi-autonomy is possible. If you go to Silicon Valley, you see Tesla roaming around in the freeways. Most of them on the freeways are going by themselves. So there is a driver there, they're supposed to keep their hands on the wheel, but they're going alone. And again, the vehicle is more and more going to be customized to a particular use. So investment, we said. Renault Nissan just announced January 27, $26 billion investment in electrical vehicles. Now, that's just one car company. So if you compute the integral, there's probably hundreds of billions of dollars that are being poured into the electrical field. So, what are then the mega trends? And this slide that I borrowed by a friend of mine who was the head of the electrical department at BMW, then he became the head of the electrical department at General Motors. So we kind of moved together from one company to another. So the trends are obvious: autonomous driving, smart connected vehicles, digital services. Now, this is important. Now, if you look at, for example, how much money we spend on our cell phone, is about the cell phone? No, it's about the services that we use, right? Same thing for a laptop. So the question is, for car companies to make money, it's not enough to sell the car itself. You have to think about what you can put in the car that you can ask people to pay for. Software-defined car. Now, this one is an important element in the sense that I can point to some cars that you can customize in terms of a driving feel. So you can have a feeling of driving a Formula One car or a Fiat 500 just by software. You change the software setting and you change completely the behavior of the car. So that's the reason why it's called software-defined car. Smart traffic, we always been, in traffic jams, and that's very, unsettling. So we would like to get rid of traffic jams. Now, there is a small problem, though. So I was in a traffic jam because there was an accident just a week ago, on the street of California, right? So 580, there is an accident. So you should take an alternate route. So, of course, Google Maps, what does it tell you? Take 680, so you go to 680, traffic jam. Why? because everybody was told the same thing. So everybody went from 580 to 680, and you get a traffic jam. So it's very interesting that you cannot solve the problem locally. So you have to have a global look, and you have to distribute then the traffic in such a way that the integral of the time spent in the traffic jam is minimized, which requires some sense of centralized decision-making that is taking place. So not many people talk about that, but you should keep in mind that that's the only solution if you want to solve a smart traffic problem. New entrants. So we will see that the most successful entry points today in the car, in the automotive industry, is Tesla, right? Is Tesla a car company? Yes and no, right? So for me, it's more like a quote-unquote software electronic company with a steel dress, right? And if you look at don't look now, right? Because of the war, because of this and that, up and down, but look at December. Now, in December, the market capitalization of Tesla was more than the sum of all the other car companies, all of them, right? Toyota, General Motors, Ford, the sum of them. So that is kind of what? And they are not making that many cars, right? So why is the market capitalization so high? Because people see that the future of the automotive industry is what Tesla represents. And so now, guess what? Everybody's trying to copy Tesla, right, of these traditional companies. So new entrants is important. Sustainability, of course. So one of the big push towards electrical and towards hydrogen is due to sustainability, which is a big issue for the young generation. So the challenges then are autonomy, first and foremost. The investment in autonomy is immense. It's almost the same as in the electrical powertrain. Functional safety, so you want to make sure that a car is functionally safe. What does that mean? That something bad happens, some part of a car breaks, some issue occurs because the batteries go bananas, there is a path to safety. So you always have a way of preventing the bad stuff, right? Then cybersecurity. Now, if you have a car which is globally connected, then one of the big issues is what happens if a hacker comes into my car? And we'll look into it in details. And that is a really serious thing to worry about. The exponential rise in functional content, so the car does more and more and more and more, like our laptops. And then looking at the life cycle management. So a car lasts for many years. I myself, I'm driving a car which is 12, 13 years old. I love it. I'm not going to sell it, so it's going to stay with me. But I have to worry about maintenance. I have to worry about, what can go wrong and how I should take care of it. Now, one of the things that Tesla has taught the world is about continuous upgrading of the quote-unquote product of the car. So every single night, you are going to get an upgrade on the software of the Tesla car. Every single night. So if you look at my poor car, every year, maybe it's going to have some update or upgrade. But here you have a completely different dynamics. And so in anything that is software defined, that is the normal dynamics that you have to think about. Because you can change. And so if you can change, use that potential to do something better. Now, one big word, right? How many of you have heard of digital twins? Everybody, right? So in any publication, everybody is talking about digital twins. Now, what does it mean? I mean, we did this 50 years ago. It's simulation, nothing else, nothing more. So what you want to do is that you want to develop your strategies and everything on the computer instead of developing it with prototypes and the like. Because much faster, much more flexible, and cost less. So it's obvious that you will need to go there. Of course, we always love something that has a new name. So digital twins is about new name. There is nothing new. It's simulation, using mathematical model to represent the reality. Okay, so why is that all this, worry about autonomy and all of that? Well, this one is a slide that comes out from McKinsey annual report about a variety of things. So if you look at the autonomous, near autonomous vehicle, it's something like a $4 trillion impact in the world economy, right? And if you look at the other things that we know, cloud technology, advanced robotic, Internet of Things, you have trillions and trillions of impact of the new technology in the world. So no wonder that most of the investment in the United States going to these sectors. Right? That's what is going to change. Plus, the other big, gigantic sector is health, especially what is open up mRNA and CRISPR-Cas9. So all this kind of stuff is as important as what you see here. But this is in our fields where the money goes and where the research also is. So about the autonomous, near autonomous vehicle, you think it's something new? No. Actually, the first time that I heard about autonomous vehicle was when I went to Berkeley, 1975, right? So not yesterday, 1975. There was a presentation in our department of the PATH project of the state of California who said, we are going to try to develop autonomous cars. And so the experiment then, we didn't have electronics to do it, right? So we had some electronics, but not all what we needed. So there was a lane of the freeway between San Diego and Los Angeles that was barred, and then only autonomous car could go. You know what this autonomous car were doing? So they embedded a conductor on the pavement of the lane, and so the car would sense that and will follow it, right? So it's like the cars that you give to your kids at Christmas, right? So they follow something that is on the ground, right? Because we didn't have the sensors or the cameras to be able to investigate the environment, so the only connection to the environment was this wire, if you like, embedded in the tarmac. But it was there, right? And since then, we've been making constant progress. Again, software, algorithms, control algorithms, the idea of smart traffic control was already there. And there was some very interesting finding that said that cars in a freeway move like a fluid in a pipe. And so when you have a traffic jam, you actually excite a vorticose movement, right? It's vortices that are very bad for getting flows through a pipe, right? So there is too much pressure. We know at some point you have these vortices that create, also in air flows, and this is very damaging, right? So same story. So to understand how the traffic moves, we, actually a colleague of mine, Praveen Varaya, used a partial differential equation and fluidodynamics to see what was the evolution of traffic. And so instead of having molecules, you had cars, but the dynamic was the same. So it's not a new idea. But then at some point, role of DARPA. DARPA is Defense Advanced Research Project Agency. Now, they have the dark side, which is money invested in armament and the like, but they also have a big chunk of money dedicated to fundamental research and game-changing research. And generally, the way it goes is that they pose a challenge problem, and then you see if you can resolve it or not, and that is intended to change radically an industrial sector or an environment challenge and that kind of stuff. Now, remember that the internet is the outcome of the DARPA program in the 1950s. I mean, we're talking about immediately after the Second World War. So it's a long, long, long impact. The other thing, what we did, right? So the introduction of automatic design of electronic circuit was a DARPA project. It was called the Vlsi Project. And parallel computing, DARPA again, in the 87 timeframe. Everything that has to do with deep learning roots into DARPA. Well, in particular for autonomous driving, they did the first grand challenge was to drive a small car in the desert and see how long this car would go before stopping or braking or whatever. Now, they were able to drive about 7 miles, and then something would happen. A year later, the challenge was raising the bar and say, you have to drive in an urban environment. Guess what? They were able to do that. And it was a combination of work done by Carnegie Mellon and General Motors. You don't want to drive in a car like that because there was no space for humans, right? It's all wires and computers. But they were able to do, a 150-mile route. So now, if you move fast forward to what it is today, now we have millions and millions of miles that are driven in autonomous fashion. You have accidents as well, by the way, and we'll see that. But it is now becoming possible to drive for a long stretch of the freeway in full autonomy, as we were saying before. I mean, Tesla does that all the time. Okay, so that is the reason why it's important. So autonomous driving, the entry of new players. So this one are the autonomous cars that you see around, and you see these waves are essentially the sensors that determine where you are and what you're doing, what other cars around you are doing. They look pretty ugly. They have that kind of a funny thing on their top. Not all of them do. Tesla does not use that kind of device. That device is called LiDAR and is laser-based and give you a three-dimensional notion of what is around you. And it is definitely a better way of considering what is happening around you than other technologies. So you hear about level 1, level 2, level 3, level 4, level 5, right? Autonomy. And so this is all about the functions that you expect a car to have. So most of the industry today is between level 2 and level 3. Some people start having level 4, but the dream is to have level 5. And this is all related to the presence of a driver and the importance of a driver to be able to take the car in his hands. And so you can see all the features that each of these levels have. And again, it's obvious that level 5 will be fantastic because you don't need to have even a steering wheel. So it's going to go all by itself. Are we there yet? Probably not in the next 5 to 10 years. But that's the goal. Everybody is targeting that level. Are we at level 3? Yes, Tesla is definitely level 3. Some of the Waymo cars are there. So there is a number of companies that are working at that level. So the important thing is that the first time that somebody really was serious about autonomous driving was Google. And so that's a new entrant, right? All of a sudden, an electronic company says, I'm going to do autonomous cars. Now, what was their goal? It was not to make an automobile. It was to make all the electronics that would make an automobile that you can buy from any of the OEMs autonomous. And so they developed a number of innovations in software, but also in terms of seeding the LiDAR market. So the LiDAR was a fundamental aspect of their approach. Unfortunately, it costed $150,000, right? And so the cost is prohibitive using this technology. Now, how much does it cost today? Well, it's projected to go down to about $10 with respect to $150,000. And how come? Because there is industrial interest. So if there is a learning curve, you're doing things better and better, smaller and smaller, more accurate, everything. Okay, now, but Google is not over yet. Remember what I told you about cyber physical system? So Google is all over this cyber physical system idea, so much so that they bought a thermostat company, Nest. So the smart thermostat that you buy in California are Google. And why did they want to do that? Because they wanted to control the environment of your home. And so it's like the brain that controls the functioning of your home. The other thing that they did is that they bought the most advanced robotics company you could find. It was called Boston, it is called Boston Dynamics. Unfortunately, they were not able to manage it that well, and so they sold it to SoftBank. And now, again, Boston Dynamics is very, very advanced, but it's very, very expensive. So is the future of robotics there? I don't know. But robotics is definitely another big investment domain. Now, you can imagine that, for example, an autonomous car is a robot, isn't it? So you can see also that there is a convergence of technologies and industrial domains. Now, okay, Apple is forming an auto team. Now, that was in 2015, right? September 21. It was a very secret project. Then later on, it was called the Titans Project. Are they doing it still? Secret, but they are. And so I'll show you some of the interesting thing there. Uber woke up and said, wait a minute, if the future is about autonomous cars, what do we do with our platform? We are host, right? Because it's going to go, but maybe not. Why? Because if you have autonomous cars, you can imagine a future where cars are roaming around like taxis, aren't they? And then you don't need to own a car any longer. You just ask it to come and pick you up. It's autonomous after all. So, but that is a platform play. So my platform that puts the consumer and the service provider in close contact. So you match demand and offer. They say, we can even improve our presence in the market by offering autonomous cars. And that's the reason why they invested a lot on this domain. Now, FCA, that was before becoming Stellantis, was a Fiat Chrysler Automotive, did a sharing of responsibility in building autonomous cars, which is something that is happening on a very strong basis. So traditional car companies and innovators coming together to try to bring autonomy to the market. So BMW, driverless car tech with Intel and Mobileye, and so on, right? So this GM has bought a few years ago Cruise for billions of dollars, right? More than $1 billion. Ford has invested in an AI company more than $1 billion. So that seems to be the standard ticket. If you want to enter into autonomous cars, you've got to pay $1 billion to get in close contact to one of the startups. Remember what I said, the innovation comes from acquiring startups. There you have it. So, but it's not only in that corner, right? The automotive companies trying to buy and innovate, but there is also the traditional semiconductor companies that got interested in this market, and so there is a strong consolidation in the automotive IC suppliers. So NXP and Qualcomm, even though this was not approved by the antitrust, and so it got undone, but the fact that Qualcomm wanted to acquire NXP is definitely possible. Samsung, I was involved in this situation, has bought entertainment companies for automobiles, right? So Harman is the largest such producer, and they paid $8 billion. So we remember, say, $1 billion is the way to enter. No, now it's becoming $8 billion going up, right? So, which implies that things are heating up. So Intel bought Mobileye. Mobileye was a startup in Israel. It was providing an infrastructure to do semi-autonomous driving. It's essentially a vision processing technology. So they bought this company for $15 billion. You see, 1, 8, 15, right? So it's like the Moore law of capital in action. And why did they do so? Well, because it is, all of a sudden imagine, now I have autonomous cars, right? So what do people do in cars if they don't drive? Well, they may watch movies, they may work, they may do all kinds of things. Now, how big is that market? Well, an estimate is going to be 7 trillion passenger economy. So you see that all of a sudden things change. And now you see that this kind of billion-dollar investment are small with respect to the potential. Now, they may or may not develop this way, but at least there is someone who thinks that may happen. And so that justifies all this investment that we saw before. However, as always, an unproven technology is going to have a problem. So someone is going to have an accident, and in fact, it did happen. Now, there is one thing, though, that I would like to underline, which is also important to put things in perspective. How many people die per year of a traffic accident? Any guess? Many, but a guess? No one volunteers a guess? Okay, I'll tell you what. 1.2 million people die, right? 1.2 million people per year, right? So not good, not good at all. So the problem is that if you indeed look at the reason why accident occurs, 80% is because of human error. You have an autonomous car, this disappears, right? There is no more human involved. Hallelujah. We reduce, for sure, the accident by 80%. Maybe some is not because the software may be faulty or something like that, but it's going to be not 1.2 million dead people, right? But the point is that we always are ready to exonerate a human. Or say, oh, poor guy, fell asleep. Yeah, but he killed 5 people, right? Or, oh, poor guy was distracted because he was on the phone. You know, right now, the number one cause of traffic accidents is people texting on the damn cell phone, right? And before was drunken driving. Now, drunken driving, you can do something about it, because if you get the guy who is driving drunk and you put it in jail for X amount of days, and I guarantee you that the next guy around is not going to risk it, to chance it, right? But texting is very difficult to catch. You cannot do, blow here. Ah, you were texting. No, unfortunately not. We don't have such a test. So, well, we do have accidents, right? Some of them are due to the fact that people overtrust the technology. So we say, oh, fantastic, Tesla drives alone on the freeway, so why don't I watch movie, right? You're not supposed to, you know, it says all over the place that you should keep your hands on the wheel and all of that, but people tend to be over-optimistic sometimes, and then guess what? Accident happen. Very few compare, right? But if you say that you have a machine that is substituting a human, you are not forgiving the machine. You want the machine to do the perfect thing. So any mistake or any problem in the autonomy domain or in any automatic control of any sort is going to be a serious issue. And it's going to send back the technology for a while. So this is what happens, right? So the first Tesla crash was in Florida, if you remember. The famous accident was a white truck, and the Tesla went under the white truck, and so he killed the passenger. Now, the passenger was watching movies, as I said before, so he didn't pay attention to that. And the reason why the Tesla went under the truck is that it had sun pointing directly to the car, and the technology that Tesla was using was cameras. And so cameras get blinded like our eyes. Less, but they do get blinded, one. Second, the truck was high, and so there was a miscalculation, so I can go under. It was like a bridge, right? Not in the cards, right? So this was the main reason why this happened. So then the NTSB did all kind of analysis up and down, right and left. Now, they couldn't say really what happened and whose fault it was, which is kind of, oh my God. But on the other hand, the outcome of that analysis was that Tesla was collecting every single byte of data of what its cars were doing. Now, why is that important? It is important, because if you want to improve the way in which your car works, you have data. And so you can say, look, there was this turn in this particular street, and that turn is dangerous. We almost went out of the road. So what is the fix? One is you fix the handling of the car, because you know that this can occur. Or second, you record that if that corner is a dangerous corner. So every time any Tesla car goes there, you say, oh, this is a bad spot. And so it will automatically limit the speed and this and that, such a way that the accident doesn't occur. So the major wealth of Tesla is in the data. Is what we always say, that the tremendous value of data. They're collecting everything in the car. Now then, after all this accident, oh my God, autonomous doesn't work. So Apple said, okay, we are just stopping this project. Not true, but there was this consideration. Uber said no more, because the crash of Uber was actually not as complicated as in the case of Tesla. So Uber said maybe we shouldn't do that. But then Uber resumed self-driving project. So it's stop and go. Oh my God, accident. Everybody, ee! Why? Because of liability. It's very expensive to have an accident that could be said it's due to your technology. And again, Apple, right? So all of a sudden, Apple started saying, well, it's not true that we abandoned the project. And the latest news are Apple accelerates work on car project aiming for fully autonomous vehicle. When is this article? November 18, 2021. Okay, stop and go, stop and go. So Apple now is start leaking this information, because it's supposed still to be very secret. But this is Bloomberg, right? So it's a big publishing entity. So how did they know that this was happening? And they are pushing for 2025 car debut, which is in a couple of years. Notice, car debut, what does it mean? That they not only do the autonomous stuff, they also do the car. So they are becoming full OEMs. Okay, so this is a nightmare for the General Motors, the Ford, the Stellantis of this world. Because now you have someone who's competing 360 degrees. So you cannot even partner. He's going to take your place, hopefully, for them. So the status, question mark, because it's kind of in the noise, but it says it's now focused self-driving capabilities, and they want to have an electric vehicle. Guess what? They say that the core work has been done, but notice it says on the core processor. Now, Apple, a few years ago, started designing their own chips. So the record for the largest chip in the world is Apple's. It's called the Monster chip. When it came out, it had north of 5 billion transistors. 5 billion transistors. Now, I'm particularly proud of the 5 billion transistors because you can claim that this kind of advances can only be had by tools. And tools, who is providing these tools? Hey, hey, you know, the technology, hey, hey, right? So that's the reason why I'm very happy about it. And in fact, it's interesting because this opened the door to all kind of interesting stuff. So Apple is focusing on safety, again, and Apple is accelerating its car development. And so the full car, you know, the car with everything in it, is going to come out, hopefully, by 2025. And then all of a sudden say, okay, now we produce autonomous driving cars, electrical autonomous driving cars. Who is going to buy it, right? And this is the economic disruption. So if I have an autonomous car, as I mentioned before, when Uber started thinking maybe we should be involved, do we need to own a car? Now, quiz. How much time in the average people use their car? So suppose 100% makes 7 days a week. So how many, what percentage the car is parked? Do you have any idea? In the average. 80%. 80% of the time of lifetime of the car is being parked. So what does that mean? Huge investment for little use, opportunity to improve it, right? So other social cost. Now we have to provide a parking place for all these cars that are parked all the time. Right? So we reduce the number of cars. We can reduce it, to have the same service as we have today, we could divide by 5 and we get the same service. So we reduce the number of cars that are parked by 5 times. So that's pretty good. And so that's the reason why you start thinking, okay, what is the business model here? So it's called the robo-taxi, is the taxi that goes around, pick you up, and so on. And so the idea is that you, instead of buying a car, what you buy is a certificate that will allow you to call a robo-taxi, and then it's like a ticket, a card that you get when you want to use a public service. It becomes a public service after all. And so it's changing completely the game here. And so if I am a maker of an autonomous car, I have to figure out how am I going to sell the product. But maybe I'm not selling a product, I'm selling a service. So all of a sudden, the economics of car making is disrupted, completely disrupted. You have complete different way of looking at it. Now, all of this is made possible by electronics. And so there is also a lot of excitement about the sensor, the processor, the architectures, and the methodologies for designing these things. Some example. If I have an autonomous car, now, what are the 4 fundamental questions I have to ask to be able to drive autonomously? So first one is, where am I? I am a car that is completely independent of humans. And so where am I, right? I'm in this corner, in that corner. Now, what kind of technology do you need? Of course, GPS, right? GPS is the most important technology that is in the location services, right? So that definitely you need that. There is also, airplanes, they work with GPS, but also with inertial sensors. The inertial sensors say, well, I was here, I'm moving at this speed, so hence I must be there, right? So inertial is very accurate. The only problem is the drift component. And GPS doesn't have that because it's an absolute reference system, right? So the combination of the two is the ideal situation, which is for airplanes. And then mapping technology. So Google wealth is mostly, in addition to their software and so on the mapping technology. Google Maps is probably the most important element of the revolution that we're witnessing today. And in fact, Apple has bought a mapping technology. So you have also the Apple Maps. Is that as good as the Google Maps sometimes? Sometimes no. I mean, that is an important part of the equation. Now, the next question that you have to ask if you want to drive autonomously is what is around me, right? So do I have a car on the right? Do I have a car in the back? Is the car in the back moving faster than I am? So that is another basic question. So how do you solve that? With vision systems. And vision systems are cameras, lidars, radars. Now, this is another very important component because that is what makes an autonomous or semi-autonomous car much better than humans. Because how many eyes do we have? 2. How many ears? 2. Can we see in the back? No. Now, a car can have as many eyes as you want, right? So you can distribute sensors all over the place. Bingo, right? So they are intrinsically better than we are. And so radars, lidars, camera system. And then people have to recognize what they see. Is that a car? Is that a bicycle? Is that a tree? Is that a person? Is that a rock? And so you need image recognition. And image recognition is probably the only sector where neural networks and machine learning have proven to be good. And all other, sometimes they are not. Why? Because all approximations, right? So anything that you do with machine learning is about building approximate models. And so sometimes they get it, sometimes they don't. And they look at the past. So you record what happened before and you try to forecast the future. Now, would you ask an AI machine to say who is going to win the European Championship in football? I wouldn't, you know, because there are too many elements and chance, right? So there are so many applications that are characterized by that, which is very difficult to imagine AI to work everywhere. The next thing to ask is that, okay, given that I'm here, that around me there are all these objects, what is going to happen next? So is this car going to cross my path? Is it going to go away from the freeway because it's taking another route and so on? So that's another fundamental question. And I have to use predictive system. Now, predictive systems are based on, again, what the people use today is on machine learning. And that is the reason why these cars, roam the street for millions of miles. Because they're trying to see anything that can happen. Because then my prediction could be more accurate. And the second thing is dynamical equation. So if this car goes this speed and has this angle, guess where it's going to be, right? And so that is standard digital twins or simulator thing. And the last and most important thing is what should I do? Given the fact that I have an idea what may happen next, where am I, and what is around me, what am I going to do? Okay, so that's the last thing. And decision system, they use neural network for decision makers. For decision making, you have connected cars that can tell you, look, around the corner there is a big hole and you may fall into it, right? That's no way in which I can find out unless someone tells me. And then the planning trip is that kind of things that I say global decision making. So this one is actually a big sensor fusion and big data. So that's the technical challenge. Okay, so to use a lot of sensor to get the information of this large sensor and then process it. So Mobileye is a company that was bought by Intel, and that is very much at the forefront of technology. On what specific aspect is vision systems. So they are the best that there is around. And they do free space analysis, driving path, they look at moving objects, they look at semantic of scene. So what does it mean that there is a guy sitting on the corner with a ball in his hands? What is he going to do? So sensors are key building blocks, and there is a lot of investment in new sensors that can collect more and more data, more and more accurately, and in a global sense. So radars, we say. So radars were very expensive components. Now you can get a radar for less than $10. So you can imagine that there are going to be all kinds of radars in a car. And then the fusion of radars and cameras. So you combine the two to get a better view. Plus LiDARs, right? So you have a full vision system with the LiDAR. And now LiDARs were that huge block over there. Now they stand on your hand. So it's a dramatic change so that you don't need to have the LiDARs up on front. And also this was rotating. There was a mechanical part to the system. But now with this new version, you don't need any mechanical part that make this object rotate. Okay, so the big issue about the construction of the car and how you put all this information technology into the car is that this is where we are. Not all of the cars, but most of the cars are characterized by a plethora of processors and software and mixed hardware software. And the original way of thinking was one function, one block. So you had a different printed circuit board for doing braking, different circuit board for doing engine management, and so on. Now, what is the evolution of this architecture? Well, this is it. From that architecture is everywhere spread around with hundreds of different components. We're going towards a centralization effort. Why? Because we have processors which are more and more powerful, so you don't need to distribute as much as before. Now, what is the impact of centralizing? That all of a sudden, the tier 1 suppliers have less space to move, right? So disruption in the supply chain. And guess what? If you look at the corner to the right, the main actor in this revolution of the architecture of the car is Tesla, okay? So Tesla went opposite to what people were doing before, and it was distributing. And Tesla said, let's concentrate. So Mobileye also started designing their own chips. And this one is the latest version that is going to come out, and it's a huge chip also, with all kind of different components to it. And this one is a Tesla full self-driving computer. They call it computer, okay? Because it is a computer after all, and very, very powerful. So you see the two mega chips in the middle, they have the name Tesla, which means that they design their own chips. And that is a key for their dominance in the factor. Okay, so this is the way in which the chip looks like. Now, this chip has also billion transistors, right? So it's extremely complex. But Tesla was not an IC maker. It's not an IC company. It became an IC company. Not only they changed the architecture, they also designed their own chip. So just 4 or 5 months ago, Ford and General Motors team up to design their own chips as well, because this is considered to be a differentiating feature. Again, to the point that electronics is going to be key even for a mechanical component like a car. Now, of course, there are IC companies like NVIDIA who is trying to mimic even what Tesla is doing, and they are trying to sell their new components into the automotive market. And this one is, again, is the actual architecture. But the interesting thing is that many companies today use NVIDIA in the automotive domain, but that is a generic chip, which not only works for automotive, works for all kind of gaming and all that kind of stuff. But Tesla has just focused on automotive, and that's the reason why it's more effective. And so, in fact, if you look at the comparison of the Tesla performance versus the NVIDIA performance, you see that there is a very large gap, okay? So, and also in terms of the time in which the chips are ready, is really staggering. So, This one is, by the way, is the Apple AV-EV timeline scenario to get to 2025 to have a first prototype ready. You see the two lines. One is the personal use cars. The other one is the fleet business model, and the prototypes are below. But if you look at the tech development, how many of that stuff is related to semiconductors? A lot. Look, AI neural chip, AV sensor system, AV software drive, and so on. You know, teleoperation software. That is the soul of the car of the future. Is all about software and electronics, sensors and computing. Okay. Problem though. How many of you have read the news, right? So, which says the chip shortage is a serious problem. And so the estimate is that in 2021, the car companies lost $210 billion because there were not enough chips to make cars. Because all of a sudden, chips become more important than wheels, right? So you must have chips, otherwise you have no cars. And so that is what is called Chipageddon. So it's the Armageddon of chips. And so how long is it going to last? The estimate is all over the map. But this also explains why there is also from European community a strong emphasis on bringing more and more semiconductor production inside Europe, right? Because of this. And notice that most of the companies that lost all this money were in Europe. So Stellantis, Renault, Mercedes, BMW, Volkswagen, they were the most of the producers that were hit by this chip shortage. Now, how come Tesla, we don't hear much about Tesla losing cars and money and all of that? Well, first of all, they designed their own chip, and they use fewer chips than anybody else because they have the monster chip. Okay. But second is that they come from Silicon Valley. The first lesson that you learn in electronics, and if you use chips, is that you have to secure the chips before you need them. Now, the philosophy of the car companies was impacted by the movement in Japan of just-in-time production. Remember, lean production and all that. And so what happens is that if I'm a car company, I'm going to order a semiconductor company chips a month before I need them. Now, assume that I have to provide chips to Apple, who is asking chips 1 year before, and Mercedes, sorry for Mercedes asking 1 month before, with numbers that I'm not sure what they're going to be. I'm going to go with him. It's safety, right? In my business model, I need to sell to him. And so there was also a lot of problems in the way in which car companies were acquiring the chips. In fact, they are changing. Everybody's changing. So they are designing their own chip and also are buying them before. Okay, so just last remarks. We don't have time to go into ethics and security, but you can recognize that guy over there. And that's when we founded Cadence and Synopsys. And you may recognize also the young guy on the stream left. Who is that? Anybody recognize him? It's Pat Gelsinger. He's the present CEO of Intel. He's the guy who talks on TV all the time that we need to invest in chips, bring back chips in the United States and Europe, right? So there is, Intel has announced $38 billion investment in Europe to make manufacturing in Europe. They are also asking a ton of money from the European community, right? Why were we there? Because we designed, it was a time in which we designed a 386, so I was part of a team to design a 386. And how? With the tools, right? We developed the first version of the tools that became Cadence and Synopsys in 1983 when I helped doing the 386. So just I want to show only one thing. So the IC design costs skyrocket. So if you look at the automotive company, how come can they design this thing? If you look at the standard chip design cost is going so high. Well, is this new way of design, new so to speak, because we proposed in 1988, but is IP-based design. And so you get the Apple, Microsoft, Amazon, Google, Tesla, all designing their own chip. You know, if I look at the list of customers of our tools, the system companies are the ones that are buying more tools and are paying more for it also. Okay, so the idea is to go piece by piece. So you get one piece from one provider, and then you assemble various pieces on your substrate, on your chip, and off you go. So if you don't do this, you cannot produce chips of billions and billions of components, and no other way. So that points to the importance of methodology to democratize the design, chip design, but also electronic design. You have to have methodologies. Now, if you look at the difference between electronics, and in particular chip and printed circuit board design, and the rest of the system industry that involves, engines and mechanical parts and so on, is like prehistoric times versus the year of the going to the moon. I mean, there is a huge difference. And so in order to be able to improve our designs globally, we need to develop methodologies that are more advanced, like what we did for chips. And so much so that even system companies now can design chips. So they are getting used to these ways of thinking about things, right? So about the ethics, and I just want to say one thing, is that suppose that you have an autonomous driving car, and you are going to have an accident because you cannot prevent it. There's no way. So you have an old lady across the street, you have a kid on the curb that is playing ball, or you have a big cliff. What do? You person, right? Who knows? Depends on your state of mind, how alert you are. You act instinctively, right? So some people will fall off the cliff, some people will kill the old lady, some people will kill the young boy, right? But if you have an algorithm, it doesn't get distracted, it's not emotional, so it's taking a decision based on some principle, right? So which one would you do? To the cliff. That's one solution. So, well, what happened is there are two ways, fundamental, philosophically, basically different to look at this problem. One is what is called utilitarian. And the utilitarian way is to choose the algorithm, right? The algorithm chooses what is least damaging to society. So in this case, it would kill the old lady, right? And there is a site, if you want to do it, just go because it's fun. In MIT, there is one site, it's called The Moral Machine. And so there is a quiz, they ask you what would you do with this and that, it's fun. And so you answer, and then they come back with some kind of analysis of what you did and how you did it and all that. Okay, so that's one way of collecting the information from people. Guess what? Everybody wants to do utilitarian choices. It seems to be just natural way of thinking. If you instead take the opposite version, instead of being utilitarian, you are based on principles, right? Guess who are they? The Germans, right? But why the Germans are like that? The best philosopher ever born were German, right? And so you say, what is the principle? The principle is that you should not discriminate on anything. And so what do? Pretty much what we would do. It depends. Flip the coin. If the coin comes up, kill the lady and kill the lady. If it comes the other way, kill the boy. Or kill yourself, right, down the cliff. It's a random choice that is in some sense not discriminating anybody on the basis of age, sex, color of the skin, whatever else, right? And so that is a principled decision. But these kind of things you have to ask yourself. Because you are doing a deterministic set of choices. And so in this particular case, it becomes stochastic. But in principle, an algorithm is unbiased, quote unquote, with respect to the emotional state and all that. So that's a basic question about the ethic principle. And security, you can make a car do whatever you want. And we were able to do that 10 years ago. You're still able to do that even today. It didn't happen. I wonder why, because it's so easy. And so now there is a lot of work going on in making cars, or in general, infrastructural system, more robust. So that's the trend there. So with this, I told you more than enough that you wanted to hear, and so I thank you very much for listening to the presentation. And if there are any questions, I'll be glad to answer.
I would like to say that Professor Tomasz Szmuc is with us. I think every one of us is a known professor, and I would like to ask to make this part of the session, which is a question and answer part, and please give us a reading for this part.
Okay, thank you. Thank you, Rector. So I should answer the question, yeah?
Yes, 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 yes. Say it again. Yes, okay.
Is there any solution adopted by Tesla?
I don't know. So sorry, they didn't tell me. I don't think that they even consider that you could have an accident that cannot be prevented. So the moral question is not even posed, right?
How would you compare the ability of our brain to this stuff that
Well, yeah, yeah.
because we have all this, you mentioned big data, sensors, our brain is operating much better still.
It is, yeah. Yeah, well, I mean, it's like we are very good at, for example, playing soccer, right? But if we had a machine like an exoskeleton that could run speed of light, so to speak, but much faster than we do, wouldn't you like to have it? I would. And the point is that instead of thinking about artificial intelligence, I always kind of think about augmented intelligence. So all this sensor, the capability of analyzing data and all of that is so fast and so much better than what we can do that we should use it, right? So for some things we are much better than machines, but for some other things we are not. So for example, today I said, okay, now how much money is the automotive company losing because of a chip shortage, right? So I put the question, after less than a second I got the answer, right? The 210 billion, right? Would I be able 20 years ago? No, let's say 30 years ago? No way. I should read hundreds of magazines to find that one information, right? So that is one obvious choice. But that doesn't require a decision. It requires analysis and then show me the data, right? And then if I say 210 trillion, I would say this is bogus, right? It's false, cannot be, right? So that's where your judgment comes in. One big application of this is medical, right? So diagnostics, right? So you come in and say, I have a cough. Okay, how many millions of diseases can be seen as one symptom being coughing? Now, you have to sift through a lot of papers, maybe, to identify this kind of strange cough. And look, your lungs don't look the same as they should be if this is the case, and so on and so forth, right? That kind of collection of data, analysis, and then it comes back and says, look, it could be either this or that, right? Then you have a way of focusing where decision-making comes into place. So you collect the information, you look at it, and then you make your own call, right? So in the health is not automatic diagnostics. So many people talk about automatic diagnostics. I would much rather have the analysis, the assistance that goes on. In fact, IBM, their AI processor, at the beginning was touted as being automatic diagnosis, not any longer. They call it again in the same vein as I said, augmented intelligence. So they provide a decision support system. They don't take decisions, right? So, and if you look at that, the way in which a boy learns, I have small grandsons, right? And I look at how they behave, it's amazing, right? So because I also know the algorithms that people use for AI, and I mean, it's no comparison whatsoever. And why is that? Because of genetics, because of the way in which the brain is put together, millions of years of evolution, you know, that kind of stuff. Will it be possible to be as good as a human brain? Maybe, I don't know. I cannot rule it out. Certainly not now.
I think that you say more about autonomous cars, but I think the more perspective in applications are autonomous robots.
Yes.
They are less challenging, but more useful in today's life.
Yes and no. Yes and no.
I think that automotive industry will block development of autonomous cars.
Not really, because if you look at all the automotive industry is investing so much in autonomous driving that I don't see any company who is trying to block it. But I mean, coming back to the robot side, talk about autonomy. Period. Right. So autonomy, even planes. Right. Planes fly by themselves mostly. They can even land by themselves. Right. So why? Because it's less complicated. There are no less things around you. There are not people walking in the sky, right, and doing irrational things. So it's easier. But autonomy is today the way in which you have planes working. Robots now. And here we come to the idea about automation, right? Not autonomous, but automation. So you do things automatically. Feedback control is a classical case, right? So, if you look at robots, when you start talking about autonomous robots, if you look at robots on the factory floor, they're mostly autonomous. Now, if you look at the robots that clean your house, that's a different story. Why? Because they are in an environment which is similar to the cars. I mean, much simpler because you don't kill people easily. But you have people around, you have objects, you have to understand the scenes, you have to understand the semantics. It's multi-purpose, you know, the whole shebang. And there is quite a lot of work going on in there, but there is no established business model. So there are some people who sell robots for Japanese companies, especially in airports, to give information to people in airports, where should go, where is the gate, take them to the bathrooms or whatever, right? So that is definitely a very specific use to robots that are in that domain. But many people think that the future of elderly people care is about robots, right? Medical care, right? But especially at home. So the whole kind of shifting of interest is, instead of taking people to the hospital, is to take the hospital to the people, meaning do whatever you can at home, because you have less social cost and you have also less cost, right? Let's face it. So, and there are all kinds of applications that are related to the monitoring of a person who lives alone, who has diseases of that kind. But if you have also and here we go into the domain of what is called human-like robots. and so they look like persons, right? The Italian Institute of Technology is probably one of the most advanced in the world about making human-like robots, and there is this iCab that looks like a kid, right? So smiling, nice, and you have also to worry about that. So if you look at Boston Dynamics, their robots are incredibly powerful. I mean, they can do things that you say, how the heck did they do that? But if you look at them, they are scary, they are monsters. Granted, they need all that complexity to make the robot not slide on a surface of the ice lake. They can go down hills like this full of snow and that kind of stuff. But I wouldn't like to have one of these guys around, right? Not in the least. But if you look at iCab, I mean, he's nice. He's always smiling, this little face. And that is very important also for the elderly because it gives you the feeling of having, like pet, right? Like a pet, not the same, of course, but they have that feeling of not being alone. So you have somebody to talk to, right? And in fact, I'm amazed. So my sister-in-law, who is a professor in engineering, bought this thing, right? And the cleaning robot, right? The thing that goes around, and she talks to it. And she said, no, don't go there. Go here. Oh, you're nice. You clean up. I say, Gabriella is a machine. Oh, but it's so nice. Bingo, right? So it's just our natural feeling of talking to things that do things alone, right? By themselves, because they look like they have decision-making and they have a personality and so on and so forth. And in general, we don't have a nasty personality because you program it. So they are very nice always, hopefully.
You presented thousands problems which should be solved. And I think that it is a chance for democratize research,
Yeah, Berkeley. Yeah.
For instance, in system dynamics.
Oh yeah, absolutely.
Chip production, no. It's very
Specialized.
production, but like system dynamics analyzing, deep learning, neural nets for image recognition, and so on and so on. But how to make links between problem leaders and the problem makers, solvers.
Yeah. Well, I mean, they.
How make the links? Because there are many people, young, old people, who would be involved in such research.
Yeah, sure. Well, in some sense, we do have that, but there's right. Well, there is such a thing. It's called crowdsourcing. Crowdsourcing, you pose a problem, and then you let people come with solutions on the web. So it's like crowdfunding. So you say, I have this startup who wants to invest $10 in it. The same thing. So there are these platforms, and crowdsourcing is DARPA. Okay, so I was part of a DARPA project where they ask everybody to design a vehicle. And the idea was also to have the vehicle manufactured in China, right? I mean, DARPA, manufacturing in China. Well, that was the idea. So we did find very interesting ideas coming from whoever, right? I mean, because you put it out there in the open. And so combining then the various ideas and building an autonomous vehicle, by the way, it was really a nice phenomena. Some companies, design companies, do that now for normal. So the winner of the crowd sourcing will get paid. But it's like an open competition. Everybody, do you have an idea? Throw it there. And so the democratization, call it, of research, I would say even of design or product development, is already there. Now, to make it super efficient is a different story, right? Because then you need the integration of different ideas and all that. The other point, which is I think we go very proud at Berkeley, is open sourcing everything we do. So, I mean, I bet that some of you are not as young as some others, but they may remember the Berkeley tools, right? So Spice and Miss and Espresso and Timberwolf and all of this. Free for all. Did we ask 1 penny for it? No. What did that do? It created also an industry, right? Because the Cadence Synopsys mentor and so on use this. But also the design companies. So Intel, what you see there, they were the last to buy tools outside from Cadence and Synopsys. But originally, they were using Berkeley tools, adjusted for their needs. And so that is another important thing. In the university, in my opinion, an important role of university is to make the knowledge as widely available as possible, right? And then, we were at a certain point in time, my department is pretty much the same position, to RISC-V, right? It's a big thing about microprocessor development. It's free, it's open, the architecture is open. You don't need to license it. And so, because the idea is that your work has much more impact if you leave it open, and then it can lead to more and more developments. It doesn't imply that you cannot make money out of it, but it let everybody participate to this, and the best guy wins, right? So that's more or less the view. But in the universities, this is not the case, because you have a technology transfer offices, right? And the technology transfer offices are always geared towards how can we make money for the university. Now, from my little, I don't pretend to be to have the truth, but from my little investigation, I think that many technology transfer offices have difficulties paying for themselves with the patents that they produce for the university. And then why have it? That's more or less it. But we are, Berkeley, always considered a kind of communist, right? Which is not true at all. But, the point is that this view of openness and so on and so forth is very important to us. So democratization for us is fundamental.
I have a two questions. The first one, because a different company like Apple or Tesla started to design the integrated circuits, there is a big shortage in the US for the IP designer or designer of the integrated circuits. Is a problem. And the second point is, you just show us that if we would like to design a complex integrated circuit, then we need to use a different IP blocks, yeah? And it's not so easy to integrate different IP blocks in the chip. So my question is, if at the Berkeley you teach the students how to do it?
Yes, of course, I do. That's my scope in life, is to teach this. No, okay, so let's go one by one. So first one is IP designers, right? So more than IP designer, I would say IC designers, because then you can use them to do an IP, to do the integration of the chip, whatever, right? We have a big request, so shortage comes from demand and offer, right? So, but we in all STEM, right, and science, technology, and mathematics, and so on, we have a big shortage period, right? Not only for IC design, for everything. Software, for example. Now, you wouldn't believe this, but one of my students has got a first job after his PhD, $300,000 per year, plus stock. Okay, granted, it's very good, right? But it's a lot of money. And why is that? Because people started betting against each other, right? And why people bet is because they don't have enough people to do what you want to do, right? And so you pay whatever, right? And that is a clear indication of that. The other thing is that it is become unbalanced towards software because AI, machine learning, came before the chip shortage, right? So all the young kids read the newspapers and say, oh, AI and machine learning is the future, so we need to do something in that domain. So they come and they ask to be trained into machine learning, AI, and so on. Now, sooner rather than later, the kind of job is going to, to have enough offer so that the prices go down, the number of jobs go down. In the meantime, now we have a chip shortage, right, issue, and we have all these system companies start designing chips. Apple is offering a very rich fellowship to Berkeley students to do chip design and EDA. Why? Because they don't have enough. And so it's very likely that there is going to be now in a couple of years a nice wave of people who wants to do IC design, right? But for a while it was considered, okay, IC design is kind of established, there's not much need to have more, and all of a sudden you realize, no, because of what I said, is the importance of chips in systems. So more and more people want to design that. Then, as you pointed out, it's not like a piece of cake to take various components. I have a cartoon that, in fact, I say plug and pray, right? Because in general you say plug and play, right? And I say plug and pray just because of what you said. It's not so easy to combine blocks, so you have to have a science of combining blocks. That's what we try to do. But it's not only at the actual lower level connecting wires, but it's just the whole point of what happens when I put two things together, the side effects. So the intended is that if I don't know, I pass something to him, then he was going to do something with that information, and he's producing the output that I want. May very well be that in the act of passing the information, something goes wrong, and then it goes berserk, right? So the point is that the semantics has to also to be correct. So we had a serious problem with the Mars landing because of the mismatch of the units. So part of the system was measuring meters and part of the system in inches. So 1 meter is not equal to 1 inch. And so, boom, it was a crash due just to that. And what is that? It's a communication, right? And that was a basic semantic of what one means, right? And so if I design a chip, I don't think about these kind of things. I have to think it at one level above because I just connect the information. So the one level above is the level of algorithms, if you like, in where I am going to specify everything that I use. And so when you connect up, you will see that there is a mismatch between the semantic of this guy and the semantic of this guy, and you fix it. But if you don't have that level of abstraction where these things become evident, you are host, right? And so there is a science also of putting things together. But it has to go from a high level of abstraction. The higher you are, the better it is. If you look at my last 5 years, 10 years of publication, you see a lot about contract-based design. And what is contract-based design? It's based on a mathematical concept, which is a contract. And a contract is a set of assumed guarantees, so there are two components. The assume part is that you have a model of the environment. And so I assume the environment means whatever is connected to me. Can be the external environment, can be another block. Okay. This is what I assume that the environment is going to provide me. If this is the case, then I guarantee that my behavior is correct, right? Or this is what I spit out, okay? The correct is big thing, is what I pull out, right? Now, if my assumption on my environment are wrong, then I know that I'm not going to produce something good, right? Now, if the two of us are connected, what happens is that he's providing me with things, so his guarantees, what he produces, are my assumptions, right? So I have to do the intersection between what he tells me to do and what I am expecting to see, and then if the intersection is not zero, I'm fine, right? Because then it means that we are compatible, right? So we can work together. This just to make a long story about what you can do about this connectivity or connection or talking to other components and all that, and to make it a science as much as we can. Okay. Shoot.
I listened your presentation during NATO conference about security.
Yes.
And
You were there.
and you mentioned that the security, let's say, threats are also in hardware design.
Yes.
And you mentioned also that your team was working on that. So
Yes.
could you comment something more details about that?
Yes, well, I mean, if you look at security, right? So there is security at many different levels again. So you can think about the security of the system, assume car, right? A car. And so you want to make sure that someone from outside cannot take over the behavior of the car. And most of the exploit happen at the software level. So you exploit a bug so that you, for example, a buffer overflow, and you come in and you exploit that, and then you insert things that were not there in the first place, right? So that is software security. Immediately below, not immediately, below is firmware security. Firmware is everything that goes at the device driver level, BIOS level, still software, but is much closer to hardware, right? And so then there is techniques and the like that we try to firm the firmware. And then last one is what we call bare metal security. Bare metal means at the chip level, okay? Now, there has been a very famous publications from Europe, by the way, that showed that there were two hardware bugs, call it, that could be exploited to break into a microprocessor. And these were called meltdown, and the other one, there were two, more or less were the same kind of features that you would exploit that are typical of the way in which modern processors work. A modern processor works essentially with out-of-order execution of instructions and with pipelining and with caching. So these are the places where you can kind of enter. And that was the out-of-order execution that Spectre was the other one. Spectre and Meltdown would use, right? Is the way in which you can penetrate while this is happening. And so how do you cope with this thing? Well, the problem is that the thieves, so the guys, the hackers, are always one step ahead of who is trying to fix the thing, right? It's always the case. And so the first point of defense is to understand that somebody is taking you over, right, one way or another. And so that is an observation issue. So you have to have observers of the behavior of what you have in your hands that tells you this is not expected. So there is something wrong that is going on. You can have software observers, and you can do that, or you can have hardware observers. And so what is an hardware observer going to do is going to check the content of the buffers, the content of the various memories in the chip, and is diagnosing in real time, I mean, running in parallel what's going on. And so if you see that the content of the register is not what you are expected to see, you raise a flag. And that's bare metal observability. So, and there were a couple of companies that we help, and actually both of them got sold, one to Intel, one to Siemens, that were doing observation to correct bugs, right? No difference. Instead of bugs, you check if there is something that is not expected. Now, that something is not affected could be a bug, but could be also something that an enemy is going to do to you. So, and about, for example, the embedded system security, SCADA. SCADA are the controllers that are around, for example, in energy, electrical energy distribution, water distribution, all these kind of things. they are very fragile because they are old processors, old connectivity, old everything. And so you could get in very easily. In fact, we know that a number of times, will not name names, but countries got in and disrupted the behavior of the infrastructure. Sometimes you can see the presence of, and that was the gist of my presentation at NATO, when I say, look, it's not so much about computers but it's the SCADA, it's the embedded computing, it's the cars, it's that kind of stuff. But it's much more dangerous than if you steal dollars from the banking system, right? And so that is a really serious issue. And so there are a number of companies that are trying to help in that domain, but it's like pulling here. You should take all the SCADA system around and throw them away and put something more modern to really solve the issue, which is not in the cards. So it's not a good situation to be in.
Okay, thank you. Any other question? I think that we reached almost the time for your lecture. So thank you very much once again for very interesting.
Thank you for listening to me for so long.
Thank you. And just one announcement. I invite you for tomorrow for Doctor of Honor ceremony for Professor Alberto Sangiovanni-Vincentelli, who will take place here. But of course, it will be also transmitted and accessible via internet. And so for today, thank you all the audience here and